Hello students, today we will discuss about analysis of stresses on inclined plane. In previous lecture, we have considered only the normal stresses acting on the cross section. Here you can see a diagram. In the first diagram, you can see a cross section MN of a bar AB. Here you can see a bar AB and the cross section MN, which is perpendicular to the axis of the bar. When the bar is subjected to either a tensile force or a compressive force acting along the axis of the bar. So in this lecture we will analyze the stresses induced on inclined section. You can see a section PQ here on bar AB. So generally all three type of stresses, tension, compression and shear stresses, may act simultaneously on appropriated plane passing through a point in the strained material. We'll also analyze such a general stress system and find the resultant stress on critical inclined plane, which may carry greater stresses than the applied ones. Here we can follow some sign conventions also. For tensile stresses, is considered positive and compressive stresses is considered negative here. If we are considering angle and we are denoting this angle as theta, which is considered positive when it is in anti-clockwise direction. And the sign convention for shear stresses, here shear stresses also acting on positive face of an element is considered positive if it acts in the positive direction of one of the coordinate axis, and negative if it acts in the negative direction of the axis. Similarly, when a shear stress acting on the negative face of an element is positive if it act in the negative direction of the axis, and negative if it act in the positive direction only. So here all the shear stresses you can see in this figure C, which are positive. So such positive shear stresses tend to reduce the angle between two positive or negative faces. So similarly, all shear stresses you can see in the figure D are negative. For the analysis of stresses which is induced due to uniaxial stresses, we have to consider some conditions here. The first condition is stresses on normal cross section. We'll consider a cross section MN of bar AB, which is already given in the figure number 1 or the figure number A, which is subjected to uniaxial tensile force P. You can see this in the diagram A. So just assume the stress distribution is uniform over the entire cross-sectional area. This condition is only possible when we have to consider when we will consider some conditions here. First condition for this is the bar should have homogeneous and isotropic material. This is the first condition, and the second condition is the bar should be prismatic. Third condition, when the force act at the centroid of the cross sectional area, and the last condition is the cross section is away from the end of the bar where high localized stress exists. So just assume that the bar meet all the condition so that the stress distribution across the section MN is uniform. So in that case, the stress, which is P equal to P by A, which is shown in the figure, which is shown in the stress element at point C. You can see a point C in this bar where the cross section MN is at the cross section MN, which has the shape of the rectangular parallelepiped, the right hand face of which is in the cross section MN. So the dimension of such element are assumed to be infinitesimally small. The second condition is stresses on inclined section. Here in the diagram number 1, we have considered an inclined section PQ of bar AB. Here this is the bar AB in figure number 1, and we are considering an inclined section on this bar. AB is PQ, which is subjected to a uniaxial tensile force P. So this inclined section PQ is cut through the bar at an angle theta between the x-axis and the normal to the plane PQ. You can see in the diagram. So here, since all the part of the bar have the same axial strain, so in that condition, the stresses acting on the cross section PQ are uniformly distributed, as which is shown in the figure. So the resultant of these stresses will be the force equal in magnitude to the axial force P. We can resolve this resultant force acting on the PQ into two components. The first component is the normal force N, which is acting normal to the plane PQ, and the second is tangential force T acting tangential to the plane PQ. So here we can resolve this resultant into two components, N, which is equivalent to P cos theta, and the T is equivalent to P sin theta. These force component N and T, normal and tangential force, produce normal stresses and the tangential stresses. And the normal stress we will denote as Pn, and the tangential stress we denote as Pt, which are uniformly distributed over the inclined section PQ. And these stresses are shown acting in the positive direction, that is when the Pn is positive when it is in tension, and the Pt is positive when it tend to produce anti-clockwise rotation of the material. Here, if we are considering the area of section Mn is A, so in that condition the area of the section PQ, which is denoting by A1, will be A by cos theta. You can find it through a diagram, through this diagram, that will be equivalent to A sec theta, where we have assumed that the A is the area of cross section of the normal section Mn. So here the normal stress Pn will be N by A1, that will be equivalent to P cos theta by A sec theta. So if we simplify this, that will be P by A cos square theta, that is equivalent to P cos square theta. P is the stress, small p is the stress. Now we'll find out the tangential stress Pt, that is equivalent to minus T by A1. Here we are considering this clockwise direction, so that will be equivalent to minus P sin theta by A sec theta. If we simplify this, we will find out, you can see this in the equation, we'll find out the final result, that will be minus P by 2 sin 2 theta. So for the resultant stress, if we are denoting this resultant stress by PR, that will be equivalent to under root of Pn square plus Pt square. If we simplify this, that will be equivalent to under root of P square cos 4 theta plus P square sin square theta cos square theta, and we will simplify this, we will find out this PR equivalent to P cos theta. So this is the resultant stress for the inclined section. Thank you.